Welcome to MrCScience.com's video on Dalton's law of partial pressures. We're going to talk a little bit about pressure today. Last video we talked about pressure of a gas on other objects. Now we're going to talk about something called vaporization pressure, or the pressure of the vapor of the gas and other gases mixed together. So let's move forward. Okay, first let's talk about vapor pressure. Now, you're all familiar if you leave a glass of water, if you leave a glass of water out on the counter, it will eventually disappear. So it will evaporate. So now, in order to evaporate, it has to change from a liquid to a gas. Now we know from chemistry that the only way that we can change from liquid to a gas is add enough energy that the liquid boils and becomes a gas. Now you'll say, well, it's obviously not boiling, it's sitting on the counter, it's not hot to the touch, you put your finger in it, it won't burn it. But what happens is effectively a molecular boiling. Energy from sources like sunlight, light in the room, anything that can add energy. If it adds enough energy to the molecule that the molecule itself is considered at above 100 degrees Celsius, it will gain enough energy to escape. So if we got our liquid here, if you get energy, the atoms have energy, they move around in liquids, but if you give one atom or molecule enough energy, it will escape the bound of the liquid and it will go into the atmosphere near it. The atmosphere near it then gets a vapor pressure. So not only is the atmosphere above the glass air, but it also has some additional water vapor in it. So now there's normally water vapor in the air anyway, we call it humidity, but the humidity would increase over that. So vapor pressure is the pressure exerted by the vapor that sits on top of this liquid. So that vapor, being a gas, exerts a pressure on the area because atoms or molecules of the gas are bouncing off that liquid. Okay, the different elements and molecules have different vaporization pressures. So vaporization pressure of water goes from say 20 degrees Celsius, which is about 20 degrees above freezing. It has a vaporization pressure of 17.5 torr. Work our way up all the way up to 100 degrees Celsius. It has a vaporization pressure of 760 torr. Now you may notice something. First of all, 100 degrees Celsius is what? It's the temperature at which water boils. 760 torr is equal to 1 atmosphere. So at 1 atmosphere at 100 degrees Celsius, water will boil. So the vaporization pressure also kind of links together when the boiling will actually occur. That's why if you've ever done any high altitude cooking, it boils at a lower temperature. That's because the vaporization temperature, let's say, or as pressure drops, the vaporization pressure can drop too. And so instead of at 100 degrees Celsius, you could get 90 degrees Celsius where it would reach 760 torr and boil. So, but the vaporization pressure is the pressure of the vapor on the liquid. Boiling point then we can redefine as the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So at that point it will boil. So let's relate this to Dalton's law of partial pressures. Dalton's law of partial pressures: when two or more ideal gases are mixed together, the total pressure of the mixture is equal to the sum of the pressures of each individual gas. That's a mouthful. But basically what it says is pressure total equals, say you have 3 gases, pressure of gas 1 plus pressure of gas 2 plus the pressure of gas 3. Say you generate carbon dioxide over water, then your pressure total will be the pressure of the carbon dioxide vapor plus the pressure of the water vapor over that. So seems relatively straightforward. If you can figure out the total pressure and the pressure of one of the gases, you can figure out the pressures for the entire thing. So say we combine two gases. We have, let's say we have a nitrogen gas, which is 5 atmospheres. And we combine a container of oxygen gas, which is 2 atmospheres. Now, basically we take one container with nitrogen, one container with oxygen, and those are both homonuclear diatomics. We pump the oxygen into the nitrogen container. So the size of the container doesn't change, both containers are being equal, but the total pressure then is 7 atmospheres. Okay, pretty straightforward on that. Let's add a little quirk to it though. There's something called a mole fraction. So a mole fraction is just comparing moles. So they define mole fraction X as equal to the number of moles of the compound you're looking at divided by total number of moles of the entire mixture. This is called a mole fraction. So it seems kind of basic, but it's actually kind of useful in partial pressures because it allows us to relate moles into the equation. So now we can figure out our masses going in there. So, but mole fractions are, say we have a mixture of gases, and let's say we have 3 moles O2, 5 moles nitrogen, 1 mole carbon dioxide. So mole fraction, so X for O2, our mole fraction for O2 is our number of moles of our compound, 3 moles O2 over our total moles. So if we add all these up, 8, 9, we got 9 moles. Gives us a 1/3 or 0.33 dimensionless because moles and moles cancel out. And really this can be related to percentage. This is also the same as saying 33%. Okay, X, so the mole fraction of nitrogen equals 5 moles N2 over 9 moles equals 5/9. Or if you convert that to decimal, 5/6 or 56%. And finally, mole fraction of CO2 equals 1 mole CO2 over 9 moles equals 1/9. Or if we do the math, 0.11 or 11%. So that's the mole fraction. So this is useful because we can use it in our Dalton's formula. We can say that now our individual P, so remember our Dalton's formula is total pressure equals P1 plus P2 plus P3 plus how many ever more gases you have. Well, our P1 can now be written as P1 equals our mole fraction of 1, which gives our percentage, times our P total. So our total pressure times our mole fraction will give us our P1. So this is useful now because we can relate directly moles or grams into our Dalton's formula here. Let's go back to our carbon dioxide and water vapor mixture. Let's say we can measure our carbon dioxide and we have, let's say, 40 grams of carbon dioxide. Then we have our water vapor, it's over water. And let's say we have 18 grams of water. So we can figure out using this or let's say our total pressure. Our pressure total in the system is measured at, let's say, 1.5 atmospheres. So we can figure out how much of that is carbon dioxide, how much of that is water. So first thing we need to do is convert this into moles. So we know 1 mole CO2 equals carbon, which is 12, plus 2 times 16 grams for the oxygens. 32 plus 12 is 44 grams. So if we take our 40 grams of CO2 over 1, multiply it by, we want moles, so we know 1 mole equals 44 grams. We get, let's grab our calculator, 40 divided by 44 equals 0.91, we'll say. So we've got 0.91 moles CO2. Do the same thing with our H2O. 1 mole H2O equals 2 times the 1 grams for the hydrogen plus 16 grams for the oxygen equals 18 grams. Oh, I made that one relatively easy, didn't I? 18 grams over 1 times 1 mole equals 18 grams. So we've got 1 mole water. Okay. So now we can figure out our mole fraction for each one. So our mole fraction of CO2 is going to be the moles of CO2 is 0.91 moles divided by the total moles. So 1 and 1.91 is 1.91 moles for the total thing. So if we go back to our calculator here, 0.91 divided by 1.91 equals what? 0.476. 0.476. That can be represented as, part of 1 or 47.6%. Our X of our water, our mole fraction of water equals our 1 mole of water divided by 1.91 moles total. And we're going to get a number similar. 1 divided by 1.91 equals 0.524. 0.524. So there are our mole fractions. We've got that. So now we can figure out our partial pressures for each of these. So our partial pressure of carbon dioxide is going to be equal to our mole fraction, 0.476, times our total pressure, which is 1.5 atmospheres. So 0.476 times 1.5 equals 0.714 equals 0.714 atmospheres. Our partial pressure of our water is going to be our mole fraction, 0.524 times 1.5 atmospheres total equals 0.524 times 1.5 equals 0.786. 0.786 atmospheres. There's your partial pressures. Now if we go partial pressures and we know our mole fractions, we can work our way backwards. Or if we got our total pressure and our partial pressure, we can work our way backwards with moles and we can get the actual grams of the gas involved. So See if there's anything else I'm missing here. So that is Dalton's theory or law of partial pressures. So if you have any questions, feel free to drop me a line at mrc@mrcscience.com.